Hi, everybody. We are now going to see a very cute context-free problem. The problem is that of deriving the language of A, B star, where the language of strings of A's and B's, where the string has the same number of A's and B's. We want a grammar for L. And it's not so easy. So I'm going to present a grammar here. Here is a grammar. S goes to epsilon, S goes to SS, S goes to A as B, and S goes to B as A. Now I claim that the language of S is L, but it's not clear what this works. It requires a proof. If it's not clear, it requires a proof. And we're going to proceed with a proof by induction. And this is really an excuse for us to practice in induction. Induction is the fundamental principle of mathematics and life. And pretty much you can prove, all or most of mathematics via induction. And it works as follows. Let P of n be any claim parameterized by n. So if you want to prove that for every n, at least 0, P of n is true, then it suffices to prove a base case that P0 is true, and an induction step that for every n, if you assume that P of I is true for every I less than n, then you also get P of n. This is the induction hypothesis, the stuff in green. And you can replace 0 with any fixed value. Okay, let's give an example before we get into the grammar of how we can prove this to prove that the sum of the integers I for I that goes from 0 to n is equal to n times n plus 1 divided by 2. This thing even has a slick proof by putting dots and completing this into a rectangle and counting the dimensions of the rectangle. But we will not see that. We're going to practice induction instead. So our claim is that for every n, P of n is true, where P of n is this claim here. We do a proof by induction. So the base case P0 requires us to verify that the sum, which is 0, is equal to this quantity here for n equals to 0, which is 0 times 1 divided by 2, which is 0. So the base case is true. Done. The induction step requires us to show that for every n, if you believe that Pi is true for every I less than n, then you also obtain P of n. Okay? So how are we going to use this to prove P of n? So let's look at our sum up to n. What do we do here? We want to be able to use the induction step. Any thoughts? Okay, we're going to write this sum as the sum up to n minus 1 and then plus n. So for the first sum, I can use the induction hypothesis and I can replace it with the corresponding expression, which is now for n equals to n minus 1. So you get n minus 1 times n divided by 2. And then you sum n. And if you do some simple algebra, you get what you want. N times n plus 1 divided by 2. Done. Okay. So let's go back to our grammar problem. The language of strings W, which have the same number of A's and B's. And this is my grammar. And we make a claim that for any string, W, S derives the string if and only if W is in the language. Okay, and we first begin with the easier part, which is the only if. This is the forward implication. We're going to suppose that S derives the string W. We want to show that W belongs to L. This fact is self-evident because all the rules introduce the same numbers of A's and B's. Nevertheless, we're going to show a proof by induction as a warm-up for the other direction, which is not self-evident. Okay, so what is P of n? P of n is any string W that is derived from S in n steps has the same numbers of A's and B's. I want to prove that for every n, P of n is true. So any string generated in any number of steps has the same numbers of A's and B's. The base case is n equals to 1. What happens in this case? Well, the strings here, you only apply one rule, so you get the strings here, and they all have the same number of A's and B's. So I'm done. What about the induction step? Well, suppose that S derives a string W prime in n minus 1 steps, and then you obtain a string W in the last step. By induction hypothesis, what do we know? We know that W prime has the same number of A's and B's. And since any rule adds the same number of A's and B's, W also has the same numbers of A's and B's. Done for the only if easier direction. Again, there isn't much going on now. It seems like overkill, but in the other direction, which we're going to see now, that's really when induction helps us. So the other direction is the if direction. You have to take an arbitrary string in L, and you have to show that S derives the string. Okay? And what do we pick for P, our claim? Our claim, P of n, is that for every string of SAB of length n, S derives that string. Okay? So now n will be the length of the string, not the number of derivations like before, but the length of the string. The base case, n equal to 0, the string W is epsilon. What rule are we going to use? Well, we use the rule S goes to epsilon. Okay, so the base case is very easy. And the induction step is where things get complicated. This step is more complicated, and it is the creative step of this proof. So everything that I said until now about this problem is completely mechanical and not particularly creative. Now it's when things get creative. Now it's the creative step of the proof is when you use imagination, insight, and when things get interesting. So we need some idea, and the idea is this. We're going to define C sub I, the number of A's minus the number of B's in the first I symbols of the string. Okay, so I have a string now of length n, and I'm going to define these numbers because they're going to help me, they're going to guide my proof. Okay, so Ci is the difference between the number of A's and B's in the first I symbols. Now C0 is obviously 0, right? Because there is nothing. What about Cn? Cn is 0 also, because by definition a string is in the language, so we'll have the same numbers of A's and B's. Now we do a few cases. Okay, so C0 is 0 and Cn is 0. And this difference can go up and down, right? So I'm gonna behave differently depending on how it goes up and down. So first I'm gonna consider the case in which this difference will at some point hit 0 again. May hit it multiple times, but I suppose that at some point, some Ci, you get a 0. And W is equal to what? Can you guess? What can we do in this case? This is not the hardest case. What can you do? And W is equal to W prime concatenation W double prime, where they're both in L, right? Because both these two strings must have the same numbers of A's and B's by definition of the Ci's. And they're shorter. So by induction hypothesis, I can derive W prime and I can derive W double prime. So I can now derive W using S goes to SS. Then you can derive W prime S then you can derive W prime, W double prime, which is W. Okay, so again, if at some point the Ci goes to 0, there is a W prime here and W double prime here. You can derive these two things by induction hypothesis, and so you can derive the whole thing if you start with this rule here, S goes to SS. Okay, but then that may not happen. It may be that for every I, Ci is bigger than 0, so it never goes to 0. It's something like this. Then what happens to W? Well, you have to think about it, okay? So then W has to be of the form A W prime B, right? At the beginning, you must have an A, and the last symbol must be a B, because you never touch 0. And W prime has length less than N, okay? So because you have an A and B, A here and B here, W prime is in the language, so you can derive W prime by induction hypothesis. And so I can now use the rule S goes to A as B, and then derive W prime from S to get W, and I'm done. Now, what happens if for every I, Ci is less than 0? So it's always deep down here. This is a symmetrical case. Can you guess? What form does W have in this case? In this case, W symmetrically must be equal to BW prime A, where W prime is in the language because you have 1A, 1B, and 1A here. And the length of W is less than N. By induction hypothesis, S derives W prime. Okay, so now I can derive W by using S goes to BSA, and then you replace this S with W prime to get W. These three cases cover all cases because two consecutive CIs differ by 1. So if you're not always up and you're not always down, it means that at some point you have to cross. And because you only change by 1, you must touch a 0 here, and you go to the first case that we saw. I covered all the three cases, so I completed my proof by induction, and I proved that my grammar recognizes the language. Wasn't that cute? It's a very non-trivial example of the power of context-free languages. This concludes our overview of context-free languages, and we're going to move on to more powerful models in the next lectures. Bye.